Hi, welcome to this QuTech360. Today, I have the pleasure of presenting you David van Driel. Well, many of you, if not all, might know him already. David graduated at TU Delft in applied physics and started his PhD in Kouwenhoven Lab in 2020, where he worked on Kitaev chains. So before we start with the talk, I just wanted to mention to the people online, especially, to raise their hands if they have questions. We will give you the word and we can all hear you, so you can just go ahead. And David, the floor is yours then.
Thank you very much. Also, thanks a lot for giving me the opportunity to do this seminar. It's really nice to have this room of people that have to listen to you for a full hour. Welcome. Without further ado, let me tell you what I want to talk about, which is Andreev Bound States, and specifically their spin and charge behavior. And before I start, I would like to emphasize that if you have any questions, there are no stupid questions, please ask them during the presentation, don't save them for later. It would be a shame if you have a question in the back of your mind that prevents you from enjoying the talk all the time. So you might be wondering about the background. This is actually a carpet, as seen in CSIS forum in Las Vegas during the March meeting. And the reason I chose it is because it looks faintly ABS-like. So specifically, this loopy thing you will see later, it looks like an ABS. Okay, with that being said, let me maybe address the first question, which is in some of your minds, which is, what is an Andreev bound state? There are many possible answers to this question, and I will give you three, all of which are correct and slightly different. So the first answer is this one. Andreev bound state is a state which forms between a superconductor, lead 1, a normal metal or semiconductor, indicated by nanostructure, and a second superconductor. And the idea is that you have an electron, for example, here, that starts to propagate and it hits the interface with the superconductor. And if it's in the gap, there are no single electron states. So you have an electron, it has a momentum, it wants to go somewhere, but it's not allowed to go. So what does it do? It reflects as a whole. That's what you see below. So it retro-reflects as a whole. It starts to propagate again, and then it sees the other interface with the second superconductor. And the same thing happens all over again. The whole reflects as an electron. And in this way, you get this endless loop of reflections, which means that it's like a bound state, except now it gets a funky electron hole behavior. And it's not just like a particle in a box state, which is fully electron-like. I should also say that when you Andreev reflect, you change the total electron count in the nanostructure by 2 electrons. So it also involves the creation or annihilation of a Cooper pair, as you can see indicated by 2e there. So what is an Andreev bound state? It's a discrete state formed in a superconductor, normal superconductor system by Andreev reflections. But nobody ever said that you need 2 superconductors. You can just cut one off and remain like this. And the system which you get then is a bit more like this system. So this is an actual device in our lab. And what you see here is an indium antimonide nanowire in green, which has aluminum here on top. And you have Ti gold, which is a normal lead covered here. And in this case, you also get Andreev bound states, but only with 1 superconductor. The reason it happens is you still have the Andreev reflection at the superconductor interface, but then you have just ordinary reflection, let's say, on the other side of the nanowire. So you have to double this loop in your mind, and eventually you find a way to infinitely keep going, and you get the same kind of bound state, except with 1 superconductor. So in this case, an Andreev bound state is a discrete state in a hybrid normal superconductor system, which forms due to Andreev reflection and confinement. And these are the systems that we usually work with in our lab. Now, the third answer to the question of what an Andreev bound state is a question a person like me would usually give you, someone who does transport experiments. And the answer here is it's a subgap state as seen in tunneling spectroscopy. Now, this is a rather important concept, so I'll go into it for a bit. I drew this inset here. So you have this dashed line, which symbolizes a tunnel barrier. So you have, in orange, you have gates, electrostatic gates below the bare semiconductor. You apply a very negative gate voltage, you form a tunnel barrier, and you enforce tunneling between the normal titanium gold lead and the semiconductor. And that is tunnel spectroscopy. In this case, you can compute what is called the conductance, differential conductance, which is actually the derivative of current, as seen here, the IDV, derivative of current by bias voltage, and it shows you something that's proportional to density of states. So if you see a line in there at a given energy or voltage, I indicated here by V in microvolts, it means that you have an electronic state there. But what is very important is that you also have, let me go into the states first. How do you read such a picture? I'm going to show a lot of these. So the shaded stuff, like the purple stuff, is the normal density of states. So this is proportional to the density of states, and you see that it's flat. So this is metallic. You're above the superconducting gap. There are single electron states for you available, so you have a flat density of states. And if you go more downwards, you see the superconducting gap edge. You see finite differential conductance. Maybe you see a coherence peak, as you see in here, the peaky structures, and then it drops to zero sharply, indicating a hard gap having no states within the gap, except one state, which is your Andreev Bound state, the object of interest. And what is also very important is you see that it crosses exactly at zero. That's not a coincidence, it's particle hole symmetry. So in superconducting systems, you say that if you have a state at plus E, you always have a state at minus E. And that's what you see here. It's perfectly symmetric in terms of energy. Finally, the reason that the state goes down and hits zero is because you have a magnetic field that's on the x-axis here. So y-axis, voltage or energy, x-axis, magnetic field. And an ABS, Andreev Bound state, has a finite effective G factor. So it responds to an external magnetic field and it crosses zero energy. All right. Now, ABSs are sometimes considered to be a nuisance, a really, really, really big nuisance. And I will explain you why, because this is my first device, or one of the first ones in 2018. It's the same thing, roughly, right? So you have a superconductor here, and it hits the nanowire, and then you have a junction here, which forces tunneling, and you have a normal lead, and there's the data, and it looks quite crappy, I'll be honest. But, you know, it's my first device, so forgive me. But you see qualitatively the same features. You see a gap, and you see an ABS coming down in field. You see no states outside of it. But this was around the time that people were doing these experiments and hoping to find not something that crosses, but hits zero and sticks to it. So zero bias peak, persistent in field, meaning a Majorana. Now, what is the lesson we learned? The lesson we learned is that Andreev Bound states can almost perfectly mimic most of these conductance signals of Majoranas, almost perfectly. So here on the left, you see experimental data claiming to be a Majorana, and on the right, you see simulated data of something which is very obviously an Andreev Bound state. Big, big, big nuisance. Then people in our group, specifically Nick van Loo and Greg Major, worked very hard on improving the quality of these devices. And what you get then is data like, for example, this. So again, gap, ABS splitting, and this is a relatively long device. Long devices, think about particle in the box modes, means little level spacing. So to have something for such a long device that looks as clean like this, you have to work really hard. But then if we have high fabrication quality, and we know that if we have a less big system, we get more spacing between our states, we can also just get more confinement. And I would say that this is roughly where we are now. We're making smaller and smaller hybrid normal superconductor systems. And you can really count the ABSs, right? There are still multiple, but you can count them. So you always have the lower one process. You have some other stuff going on here. But people work really hard for it. And now we have some control over the ABSs. Which brings me to my important point, which is the fact that ABSs are a gift from nature for us. They are not a nuisance, they are a gift. And I'll give you 5 reasons why. 1, triplet Cooper pair splitting. 2, Andreev spin qubits. 3, coupling spin qubits through cross-Andreev reflection. 4, Andreev molecules. And finally, number 5, we're especially proud of, which is making a Kitaev chain, mediate an interaction through a Kitaev chain. There are many more reasons, but these are just 5. They make the short list. In any case, all of these 5 deserve a QuTech360 seminar on their own, and a majority of them did. So now is my proposition. Here it is. Andreev Bound states are the most important building block for hybrid semiconductor superconducting qubits. And I really mean it. So what I want to do here today is give you a feeling of how one sub-gap state can underlie all the physics you see here and even more. So the contents of this talk are the fundamentals of Andreev Bound states, some theory, some basic things, then spin-polarized tunneling measurements into Andreev Bound states, and finally, charge sensing of Andreev Bound states. Okay, so I told you what an ABS is, but it was a bit hand-wavy, right? With the loopy thing, and just turns back on itself. Let me give a bit more quantitative explanation, which I like a bit more, and let's build up our system. We start with a confined system, and if you read David Griffiths, you know that a confined system will have modes. But we want these modes to be slightly more interesting, so we add a superconductor on top. And now we're going to construct the level diagram. So we list energy on the y-axis, and we start adding the states we know. So counting from the Fermi level, how many electrons do we actually occupy? 0 is an obvious answer. And then you have the odd occupation, but we're at 0 field, so the spin down and the spin up are degenerate. And this is already a very nice state because it's very polarizing. Because charging energy loves this state and superconductivity hates it. Why? Superconductivity wants Cooper pairs. It wants even numbers of electrons, and here's a state with an odd number. Not good. Charging energy, meanwhile, sees only one electron. So no second electron, no Coulomb effects, just great. And if you go to the 2 occupation, it's obvious. The opposite happens. I mean, charging energy hates it because you have to pay an electrostatic energy to add electrons, but superconductivity really doesn't care. It just makes another Cooper pair. These are no longer eigenstates, because if you have superconductivity, if you write down these states in a matrix, you get an off-diagonal element, which is called delta, the pairing, and the 0 and the 2 get combined into a new state, the 0 plus 2 state, with their coefficients. And from now on, we call this manifold the singlet and the doublet. For the singlet, I'm cheating a bit. The 2 is actually shorthand for an actual singlet type of wave function, but out of laziness, I'm just going to call it 2. And the doublet, which is still these relatively unperturbed odd states, let's say. So that's my answer to this question. What is an ABS really? It is any kind of confined proximatized state. You can go into this very deeply, but we are very liberal in our use of the term ABS. Okay, let's move on. What do we expect from spin in this case? Well, we apply a field, and what happens is the doublet splits in energy with Zeeman, and the singlet is a singlet, so it really doesn't care. It does not move. Okay, this brings me to the first experimental part of this talk, which is spin. Keep in mind what I just showed you. You apply a field, the doublet splits. Here you see the same thing, but then in an energy diagram. Y-axis, energy, x-axis, Zeeman, singlet, unperturbed, doublet, splits. Now, one thing I want to emphasize super clearly is the way we observe these states in transport is through tunneling spectroscopy, which means that we add electrons, but we can only ever see transitions between states of opposite parity. So if you look at the singlet state, it's 0 and 2, and the doublet is 1, so they differ by 1 electron. And that's the only thing we can see. We never see transitions from odd to even, always between 2 opposite parity sectors. And we see them when we have an electron matching the energy difference between the 2, which in this case is given by some combination of Zeeman, the gap, and chemical potential. And now what this would look like in tunneling spectroscopy is this, something I showed you before roughly, again, energy, y-axis, B field, x-axis. And what happens then is that the ABS crosses 0. You see that crosses 0, and that means that the ground state changes, which is called the quantum phase transition. And it's a specific one. We call it the singlet-doublet transition because the singlet used to be the ground state and now the doublet is the ground state, which in our case means that the ground state has become spinful, which is pretty interesting for a superconducting system because they don't really like the odd occupation. Now, one thing I need to stress a bit now is, again, particle-hole symmetry. Let's look at the states before the singlet-doublet transition. We start with a singlet ground state, doublet excited state. But there are actually 2 transitions that take you back and forth. You can add a down electron. So adding electron means positive energy. So that's why you see it here starting around plus 250 microelectron volts. But you can also remove an up electron. So it's the same energy. You're creating the same state, but because of the 0 plus 2 nature, you now have 2 excitations which take place at opposite energies. And this is your particle-hole symmetry. And after the singlet-doublet transition, this reverses. So now the ground state is down, and you can either add an up electron, adding positive energy, or remove a down electron, which is here. So there are always 2 paths that take you between these 2 states, not just one. Okay. So the singlet-doublet transition can be driven either by magnetic field or by chemical potential. And after this, if you have a spin-down ground state and it's a single orbital, Pauli exclusion principle prevents you from tunneling more downspins. So you expect a spin blockade, or you do not, because there might be spin orbit, which we have a lot in our system. So the question is a bit, do we actually see good spin polarization of the Andreev Bound State doublet state? And how do we even measure this spin blockade after all? Now, the way you do it is by combining two ideas from two papers. So the first paper, I can give you a picture summary. This first paper says I have a lead with a certain flat density of states that goes until the chemical potential of the source. And then I have the density of states of a quantum dot, which is Lorentzian. And it says that an electron, which is outside of this density of states, it cannot pass. And an electron that is on resonance, let's say with the quantum dot's energy, it can pass. So this paper says that you can use a quantum dot as an energy filter. And because you're probing states at a given energy, it's like doing spectroscopy. The second paper is actually pretty fun, because you might recognize some of the names of the first two authors. This is a very nice paper from Ronald Hansen and Lieve van der Sijpen when they were working with Leo. And it says that you can have a quantum dot and use it as a spin filter in transport. Again, picture summary. You now have a source and a drain, and they differ by their chemical potential, which defines a bias window, which you can see by the dotted lines. And if you spin split your quantum dot, such that only one spin species falls in this bias window, you can have spin-polarized transport. Now, I think you probably know where I'm going. Namely, if you combine these two ideas, what you get is the possibility to actually do spin-polarized spectroscopy of an ABS. So you can energy filter and you can spin filter and you can excite your ABS only with down or up electrons at your choice. And I'm using this symbol for a quantum dot because it faintly resembles the density of states. So this is a quantum dot from now on. Okay, let's build up the system we're going to do these experiments in. This is a type of diagram we use a lot in our group. So we have spatial position on the device on the x-axis and energy on the y-axis. We start with a lead all the way to the right, and the lead is grounded because its energy is just at the Fermi level. We add a superconductor gap, we add a semiconductor, we get Andreev Bound States, we get two, right? Positive energy, negative energy. And this is your typical two-terminal device like I showed you before that allows you to do tunneling spectroscopy. But we can do better than this. We can add at least one more lead, and then you get a three-terminal device, which allows you to do more fancy stuff like non-local spectroscopy, which is not really relevant for this talk, but we need one more ingredient to have the device the way we can do spin-polarized tunneling, and that's a quantum dot, which gives you ultimately this device, which is normal insulator superconductor quantum dot normal. So you go here, you have a normal lead, which is grounded, you have tunnel barrier, you have your hybrid here, grounded aluminum, you have a quantum dot defined by your bottom gates, and you have your normal lead here. This device allows us to probe the hybrid from the left with tunnel spectroscopy and from the right with spin-polarized spectroscopy, which is very useful, as you'll see later. So what does dot transport look like? What does it look like when you use a dot as a spectrum tool instead of a tunnel junction? Looks a bit like this. So again, energy diagram. So now your dot is above your bias window, and it's in the normal density of states of the superconductor. And the thing I'm plotting here is current. So if the dot is here in terms of energy, no current. Why? Because it's outside of the bias window. There's no way for electrons to reach it. So we have to bring it down in energy. And at this point, it's in the normal density of states of the superconductor. So there are single electronic states available for it. And it's in the bias window, so we're going to see transport. And then if we bring it down even further, to be exactly on resonance with the Andreev Bound state, we see a peak. So we can indeed tunnel into this ABS. But this tells you nothing about spin. So let's add spin to make the whole thing a bit more interesting. Oh yeah, I should say that if you bring the quantum dot level below the Fermi level, it will always be occupied. And you're not going to have any transport because it's full, no electrons can pass through it. Spin. So at zero field, you have a spin-degenerate quantum dot, up and down have the same energy, and you have a singlet ground state. Now we apply a magnetic field. And what it does is it spin splits the quantum dot level. By quantum dot level, by the way, I mean the charge degeneracy point between the n and the n+1 state, for example, for quantum dot, in which you can put electrons. it usually has a very high G factor in our devices. Usually these quantum dots have a G factor of about 40. But that's not the only thing that changes, right? Like you apply a field, so also the ABS should feel it. And that's what happens. The ABS excitation crosses 0, and now you have a spinful ground state. So that's what happens. And now we can look at what happens to transport. Finite field, enough magnetic field to spin split your quantum dot. You will have one possibility. You can tunnel into this down excited state. So again, I told you there's two ways to go from singlet to doublet. You can add down electrons or you can remove up electrons. In this case, you cannot remove the up electrons because they cannot go into the lead because it's biased to be above the Fermi level. In this case, you can add down electrons because that state is empty and electrons can go this way. But if you apply more field and you drive the singlet doublet transition, it reverses. And now you can either remove down electrons, which you cannot do, or you can add up electrons, which you cannot do because you have a spin-polarized quantum dot. And by the way, the other quantum dot level, the up spin, is outside of the bias window, so it does not participate. Again, if there are any questions in the meantime, also online, please feel free to interrupt me. So now let's have a look at actual experiments. This is tunnel spectroscopy, which is non-spin polarized. And I showed you this before. So what you see here is zero field. You have a nice ABS, which splits carefully, crosses 0 here. So you have the singlet doublet transition. Ground state is singlet before, doublet after. And then some weird stuff happens later in the field. Now the big question is what this will look like for spin polarized tunneling. Like this. This is the down filter. So you're only going to see down excitations here. By the way, I added a white triangle with the high field stuff because there's missing data. You can also look at the up filter. And now what you should try to do is put together the down filter and the up filter data in your mind and count whether all the lines you see in there add up to the total as you see in tunneling spectroscopy. This is a bit hard to interpret. So what I'm going to do now is compare this device with another device. And I think you will see why this is so spin polarized. So there's two devices now. The left one I showed you in the previous slide, and the right one is another device. And let's first look at the allowed transport processes for the ABS. This one is allowed because your ground state is singlet. You can add a down electron and you reach the down excited state. Perfectly allowed. This one too, you've crossed 0. Your ground state is now down, and negative energy means removing electrons. So you remove a down electron and you arrive at your singlet first excited state. All good. And the same holds for the up spin. So you can remove an up electron from the singlet and reach the down excited state. And then after the singlet doublet transition, you can add an up electron to the down ground state and reach the singlet excited state. So this checks out. But you might notice there are some additional lines here on the device B. And those are the non-allowed processes. So let's have a look what these are. So this process, you can directly tell, it shows up only in device B, faintly, but it doesn't show up in device A, which is already interesting. Because what you're trying to do here is you're trying to remove a down electron from the singlet ground state. And this would create the up excited state, which is higher in energy. So the only reason that you see some tunneling in device B is because of spin orbit rotation. The downspin can rotate a bit into an upspin during tunneling. And after the singlet doublet transition, you should get something which is Pauli blockaded. So you add a downspin to a state which is already down on the same orbital. And this is classically not really allowed, but well, you know, you can have triplet superconductivity in these systems. So spin orbit does you a favor. It's just interesting that you don't see it on device A. And then the same here. You remove or you add an up electron to the singlet state, you arrive at the singlet excited state. And then after the singlet doublet transition, you remove an up electron from the down state, which should also not be allowed. So that's how you should interpret these. I think it's pretty cool that you can have one device completely spin polarized and the other one completely not spin polarized, while the Andreev Bound state looks roughly the same from tunneling spectroscopy. So this just shows you what you're missing in terms of spin. And you can also, like I said, drive the singlet doublet transition with chemical potential. And now this looks a bit loopy, and we tend to call this cat eye shape. Remember the carpet, this is what it looks like a bit. So now you drive the singlet-doublet transition twice, actually. You start singlet, the loop is doublet, you get singlet again. So now let's have a look at the spin-polarized tunneling again. This one I find especially nice because what you see here is you get only one of the lines, really, and also the other. So this is, I think, a very clear measurement where you can see that you can really dissect tunneling spectroscopy in terms of spin using quantum dots. And then there's one thing that I've been hiding from you a bit, which is relaxation. So we've been discussing always excitation of the ABS with the quantum dot, but it has to relax back to the ground state to complete the transport cycle. And how does it do it? That's why you need this second lead. So this left gold lead is just a tunnel junction, and it's not spin polarized or anything. It's also grounded, so it's going to accept every type of exchange. It's going to accept removing and adding electrons. So you may ask yourself what happens to your ABS transport if you block this way of relaxing the ABS excited state. So first, let's look in tunneling spectroscopy. So y-axis, we have energy again. X-axis, we have this gate voltage, which we put more negative to pinch off and not have transport anymore. And I've plotted conductance on a log scale so that you can be absolutely certain that there's no transport after this blue line anymore. And then let's have a look at what happens after it's pinched off on the spin-polarized tunneling. And this is relatively interesting because I think the most obvious feature you see here is the subcap state, which is there at higher gate, and then it just disappears. But the other transport does not disappear. And that's because those other lines that do continue are tunneling into the aluminum normal density of states. You're above the gap, you're not tunneling into an ABS anymore, and it's not a spin-polarized density of states. So you have no trouble driving transport in this way whatsoever. It's just the ABS that you can no longer relax anymore. So you really need this normal lead to relax it. Which brings me to the conclusions on spin of an ABS. So quantum dots can be used as simultaneously energy and spin filters, and therefore do spin-polarized tunneling. And Andreev Bound States can show a total Pauli blockade, but they also cannot, depending on spin orbit. And finally, pinching off this tunnel junction, your only non-polarized electron reservoir completely prevents relaxation of your ABS. So you cannot drive transport through it anymore. Then this is on arXiv in case you're interested, but the thing I really want to advertise is this second paper, and have a look at the date in which it was archived, version 1 and version 2, exactly the same dates. What a coincidence. I actually knew this first author, and we turned out to be working on this simultaneously, and we coordinated these papers together. They did very complementary work in QuTech, so that's pretty nice. It works on other systems as well. And before I move on, take a breather. How much time do I have? Great. Because this will be part 2 of the talk, which is about charge of Andreev Bound States. Also now would be a nice time for questions, if there's any in between. Otherwise, yes, Jen.
How big is the thing, the island with aluminum?
It's 150 nanometers.
150.
And it doesn't really have a charging energy. It should be about 10 or 50 microelectron volts.
And the energy level should be very small. Level spacing.
The level spacing is relatively large. I think maybe 10 millielectron volts in terms of gate. So if you have level arm, that's 40%. So a number of millielectron volts. It depends on where you are. If you're in relatively low gate voltage range, you have very big spacing. And if you go up in gate, the spacing decreases a lot. Yeah. Yes, you first.
How do you know whether the device will show spin filtering or not? Do you just break the barrier to have longer length compared to the spin orbit length?
Yeah, that's a very good question. So it can happen in many places. So you can have spin orbit in the hybrid or the ABS itself. You can also have spin orbit in the quantum dot itself, because it's also 3.5. In my experience, okay, so this also relates to the previous question. You have 3 regimes. You have a regime where you have no Andreev bound states, really, where the system behaves just like a bulk superconductor. You have a regime without superconductivity, and you have this intermediate regime in which you have Andreev bound states. And if you go to one end or the other end, I guess that kind of sets how much spin orbits you have due to level spacing. Yeah. I saw another question, I think. Or
Yeah, that was very related. Like, can you tune the spin orbit coupling, or if there's spin flipping allowed or not?
yeah, you can definitely select Andreev Bound States with more or less spin orbit coupling. Yeah, in the same device, so you don't need to fab a new one, luckily.
So here to take these maps with a quantum dot, you change the chemical potential of a dot, but do you keep the bias constant? And to what value?
400 or 500 microelectron volts. Yeah, so it's above the gap of aluminum. Yeah. Charge? Yes, okay, charge. Let's go back to our favorite levels. So singlet, doublet, and now let's look at something which is very important in all ABS language, which is the dome. And the dome tells you the ground state and the parity of the ground state. So on the x-axis, you have chemical potential of the Andreev bound state. Y-axis, you have the pairing strength, let's say. And for all the people in this room that work with normal quantum dots, you're always exactly here at the bottom, 0 pairing. And that means that you can have an odd and even occupation of a dot. But as you go up, you see that the slice of doublet you get starts to decrease more and more. And that's again because of this forever competition between charging, which one's odd, and superconductivity, which one's even occupation, which is relatively interesting. But this picture you can also look at in charge expectation value, which I think is even cooler. And then you get something like this. Again, for normal quantum dots, no superconductor, nice integer charge, as you expected. And then you go up and you see that this color map starts to be a bit funky. And that's because of the 0+2 nature of the even state. So the charge is no longer really integer, which I think is pretty cool because it's a single state, which shows this behavior, which leads us to the question, can you actually measure the ground state charge in a way? And not just the charge of excitation, I really mean the ground state. And the answer is that we can. This was also my joint backbespreking pitch. So for some people, this won't be new, unfortunately, but we can measure it with a single lead quantum dot charge sensor, as they are routinely used, I guess, in spin qubit systems. So what you have here is a quantum dot, which is coupled to a normal lead, and the normal lead is attached to a resonator. So we're sending in an RF wave, and it comes back. We look at the reflected signal and the change. And what you expect for a quantum dot is a dip at the Coulomb resonance. So when you have a charge degeneracy point, you get a dip in reflected signal. Okay, this works, but then this is not something in itself. You want to use this as a tool. You don't want to study it. So you place this single lead quantum dot next to a system of interest, which for us is a hybrid semiconductor superconductor, grounded superconductor. And then you have field lines going between them, which means that if you add charge to the system of interest, your quantum dot should also feel it. And in that case, if you add an electron and the ground state changes, you should see a dip change because you're effectively gating your quantum dot charge sensor. And this is the way you can read out the charge expectation value of systems. All right, so what do we expect for charge? So I put the dome at the top right and I put us at the bottom, so no pairing. And what you see in terms of excitation energy is straight lines, integer charge. This is just an ordinary quantum dot. And if you look at the BCS charge, it's a staircase. By the way, I should probably have put a minus in front of the mu, but don't worry. Now, we can make this a bit weirder if we add superconductivity and everything starts to get curvy. So you see that the excitation curves, and also you might see some curvature around the steps of the BCS charge. But we can do better than this. We can add more curvature and more until we even don't have a doublet ground state anymore. But we still see the BCS charge changing smoothly, which is relatively interesting because what you get is a change of ground state charge without a change of ground state, which is relatively weird. So this is something we wanted to measure. Now, the system we did it in is actually the same system, but now we use RF. So on the right side, we have a tunnel junction, which has RF signal on it, and a tunnel barrier, which I indicate by the dashed line. And on the left side, we have a quantum dot. And note that I drew this schematic potential and I drew this barrier a lot higher because I really want to emphasize there is no transport between that quantum dot and the hybrid. It's fully pinched off. The only way they feel each other is through capacitance. So what do we expect for transport? Well, first of all, for tunneling spectroscopy, we get this. We see, again, energy, in this case, a gate that controls chemical potential in the x-axis, and we get the Caesar's Palace carpet shape ABS, and it looks just like you would expect for the simulation, singlet, doublet, singlet. But now the real question is, what do you see in the charge sensor? Can we actually see the ABS charge evolving for this system? And it turns out we can. So if we sense from the left with the quantum dot, we see this. Y-axis is sensor chemical potential gate. X-axis is still ABS chemical potential gate, and you see a dip in reflected signal, which moves when the ABS comes out of the gap and goes back into it. And this is a bit wonky because you don't see really big continuities, you see curvature. And curvature you don't really see for integer charge usually. But we can straighten this out. So if we apply a magnetic field, we can increase the size of the doublet region. Also note the splitting of the Andreev Bound state in field. And the charge starts to look more and more like you would expect for normal quantum dots, especially this one. They appear to be just straight lines with discontinuities. So we can really sense the charge of this ABS. But I also told you something about a change in ground state charge without a change of ground state. So we pick, oh yeah, let's do this first. So a charge sensor is a tool. And here we show you the charge of the ABS from the point of view of the charge sensor. And again, here what you see is the doublet is relatively small at the start. So this is your doublet state, and there's a lot of curvature. And as you go up in field, the doublet becomes larger, and this change becomes sharper. But now what I wanted to show you is something where you don't have a doublet ground state. So these are two ABSs at a finite field value, and notice that they never cross zero. So all of this is just singlet, always even charge. And what you see in the charge sensor is this. Now, I know it's very fashionable to add lines to guide the eye, so that's exactly what I'm going to do. And you see that the charge disperses only when the ABS disperses. And when the ABS is deep in the gap, which is here, you don't see the charge really moving around. So we can really detect this slowly changing ground state charge without seeing an actual transition, which I think is actually pretty cool. This is one ABS. And eventually what I work on is Kitaev chains, which is change of ABSs, quantum dots, superconductors. So we want to do more things. And maybe you can guess where this is going. We can actually try to do something with two ABSs, which are tunnel coupled. So if you tunnel couple two Andreev bound states, from now on you call it an Andreev molecule. It's the superconducting analog of a double dot, something that does not really exist in nature. And if you look at the charge stability diagrams, so here left is charge stability diagram and plotting difference between even and odd ground state energy. It gets also very curvy. It looks very different from a double dot, I would say. And on the right, I plot charge expectation value of one of the two ABSs. And you might see that there's a pretty interesting point out there, because you see that these are clearly interacting systems, because you have level repulsion, but you also see a crossing. Doesn't mean we have zero interaction there, or is something else going on. So now let me describe the system that we do this stuff in again. So we have, again, the charge sensor, which is only capacitively coupled to the Andreev bound state. But now what used to be a tunnel junction, we configure to be another quantum dot. And because it gets some amount of proximity from the hybrid, we call it an ABS, according to our definition. Any bound state with any proximity is an ABS. And then we can probe this analog of a double dot system in transport, and this is what we see, for example. So these are 4 resonances. So you see that this one is open avoided crossing, and this one is something different entirely. And now the really interesting question is, what happens to the charge at that point? This is what you see. So note that there is a charge transition in the vertical going from here. So what we have on the x-axis is the chemical potential gate, this fella, and on the y-axis we have the chemical potential of this guy, which we're actually sensing. So the gradient you see in the y-axis is just the ABS ground state changing. But you see some more stuff. And if we take the derivative of this reflected phase of the charge sensor, we see something like this, which is relatively interesting because it tells you that if you go to this crossing, not avoided crossing, but a real crossing, and you walk along the horizontal, or you walk along the vertical, you only see, you don't really see a change of charge, but there is an interaction. And if you then go to this crossing and you take a spectrum, so you apply a finite bias and you look at what happens, what you get is a zero bias peak separated by two peaks. Now, what you're looking at in this case is a Kitaev chain system. So we call this non-avoided crossing a sweet spot, because in these systems you have two types of interaction. You have a tunneling type of interaction and a superconducting type of interaction. And if those two are equal, you don't get an avoided crossing, but a crossing. But it's not a trivial crossing, like a non-interacting double dot. It's actually rather like a poor man's Majorana type system, where you get these operators which are their own conjugate appearing at the ends of the chain. So that's what you see. You expect a zero bias peak separated by some side peaks, which you call the gap. And in terms of charge, you expect the excitation to be chargeless. So again, the Majorana, also in the Kitaev chain, is an excitation between an even and an odd state. But now the cool thing is that the even and the odd state have the same total charge expectation value. Think about it. So that's very preliminary. At least I wanted to say most of this has been measured by Bart, which is very nice. Thank you. And this is just one cool application of what you can do with a typical spin qubit type of readout applied to hybrid systems, which is my personal biggest interest. So then I'd like to conclude about charge. A single lead quantum dot can actually charge sense hybrids. And an ABS charge can evolve continuously because of the continuously changing singlet ground state being a superposition of the 0 and the 2. And then finally, we can read out the ground state of an Andreev molecule with these two opposing type of interactions that you look for in a Kitaev chain. Now, to end, this is what I started with, all these applications. And I really hope that in my talk, I've been able to convince you that, in fact, all of this has always been ABS. And if you're looking for a PhD or a postdoc, or if you have a great master student who's looking for one, please let us know, because we need people to work with. Thank you very much.
Maybe there are questions? Questions from online?
Not yet, but if anyone has a question online, you can unmute and ask a question in person, or you can put it in the chat.
Okay.
Maybe I can ask a question.
Yes.
So in the charge sensing data, when you go through the cross, you go from, let's say, dark color to yellow color. Maybe can you go?
Yeah. Can I? It doesn't work yet. Maybe.
When you go from at the cross, you have this intermediate color, which is about red.
Yes. Yeah. Yeah.
Yeah. And so if I associate the blue or violet color to, let's say, a 0 and a yellow to a 2, the dark is more like a 1, right? If I cut vertically far away from the cross, I get the transition from 0 to 2, right? As you explained.
Yeah. Exactly. Yeah.
If I cut it at 3.5.
Well, actually, it's 0 plus 2 to 1 is what you get far away from the thing. So my point is, if you that's a good point. If you take the cut far away from resonance here, you see this discontinuous change of ground state, which is the 0 plus 2 state, the singlet, to the doublet state, which is just 1. And here it's continuous.
Okay, so on the right side, you have, say, 0 to 1 transition?
Yes, because it was taken, in terms of the ABS, yes, because it was taken here. So for the ABS you're sensing, this corresponds to the 0 plus 2 occupation, this corresponds to the 1 occupation. And that's where this cut is taken.
Okay. So
maybe I can show you in the simulated data. If you look here, you see the same thing. You see like a speck. And that's because of this poor man's Majorana appearing, which tells you that you cannot resolve the difference of parity states. But if you go slightly diagonal, diagonal means splitting, because it's the old Majorana story. You perturb only this one, the other guy doesn't feel it, and vice versa. So that means if you go horizontal or vertical, you don't feel it. But if you go diagonal, you split the Majorana in energy, and you should see a charge signature.
Okay, yeah, thanks.
Okay, then thank you everyone. Oh,
One more.
yes.
Thank you.
Can I ask the spin part, compare AB device and the transition from ground state down?
Yeah. Shall I go back or
Yeah.
take some time? So you mean the data or the schematic?
Data, device A and device B.
Oh, yeah.
So on the right, say magnetic field, high magnetic field part.
Oh,
I just wondering, you say
do you mean in this one or? So here I'm showing a bigger range. The
previous one.
Yeah.
Yes. So you say the spin blockade transition. Say the right middle color plot.
So this one?
Yes.
Yeah.
So that line, the fainted line, is from state down to what state?
Yeah, so that should give you that's a forbidden process. So that's ground state down and adding another down electron.
But down, shouldn't you cause more level spacing energy because of the level spacing?
Yeah, so I'm not writing this down very precisely, but in this case, down is your ground state and the singlet is your excited state. But because of spin orbits, you get singlet-triplet mixing. So your effective new state contains a down-down component due to your spin orbit level repulsion. So indeed, the actual down-down state, the unperturbed one, is very far away. But because of spin orbit, it mixes a bit with your singlet state.
So that should be a singlet, mostly singlet.
Largely, yeah. I cannot tell you the percentage, but I guess, yeah. That's why it's so faint, I guess, right? I mean, if it's very bright, it should be mostly triplet. Yeah. One more.
May I ask, what are all these subnet features that appear? I mean,
Yeah. Simple answer, Andreev Bound States. More difficult answer. It's a bit of a paradox, right? Like these systems have a lot of spin orbit. I show you spin-polarized tunneling, which is for device A, this one, actually very spin-polarized. But then what you also see here is a spin splitting. So this is the upspin, and you see that it sticks around the gap edge and goes back down at some point, and then this guy appears. So I think those features are related to spin orbit and other ABSs coming down, because you have some level spacing, but the Zeeman energy is quite large in these systems. And there is a zero bias peak that sticks for a while, which is a bit puzzling, to be very fair, because it doesn't obey the ABS rules. Now I have to go all the way to the other end of the presentation, but it's worth it. Hang on. What I also didn't tell you is that all those measurements are composition of two measurements, because for a given bias polarity, let's say negative voltage, you can only probe unoccupied states. You have to do the opposite bias to probe the other states. Let me show you. This is a bit more clear. Oh no.
You know the slide number?
I have it, yeah. So this is that figure, but then decomposed into a particle type. So what you see here is a zero bias peak in the down, which doesn't show up in the up holes. And I just told you that for the ABS, adding a down electron and removing an up electron is the same, but this one doesn't behave like it. So I don't know. Some people say quasi-Majorana, but I don't like throwing around these terms too much.
Do you know why sometimes it's not symmetric around chemical potential equal to zero, the transport data?
You mean that the states are not really at plus and minus E?
Sometimes minus have two Andreev state, but plus only has one.
I think that might be, if I understand you correctly, we have some bias offsets in the system. So we're dealing with microvolts. It's a relatively small thing, so it's very easy to get an offset from your voltage amplifier. Yeah.
So everyone, thank you very much for joining this QuTech360, and especially to our speaker, a big round of applause.